So the subtitle was derived from my children who thought that would be quite funny, but it's actually fairly accurate. So as one of the last remaining geochronologists in the community, and the importance of geochronologic data points for petrogenetic models and things like this, I thought it would be important to give you some idea of some of the things that go into these ages, because they're not strong points that are impermeable to any sort of transmutation. Rather, they are interpretations. And so I thought this would be a good opportunity to share this with you. So why are we so confused about the age of the moon? And to answer my own question, I think there's three main reasons. First, what the age of the moon means to different people is different. And I think some of the confusion is we are comparing, as Chip says, apples and oranges. The other reason is that a lot of the ages are based on geochemical modeling, and those models have a whole bunch of embedded assumptions, and many of those assumptions dictate the age you determine. And so you can get an age, but if it's based on an assumption that you don't believe, then it's probably not a very accurate age, although it may be very precise. And finally, many of the ages just are wrong. And so rather than pick on the community and the data that are in the literature, I'm going to pick on myself. So I'm going to give you examples of, my failures or the things that I've sort of done in the sausage making. So if there's anybody to blame for anything here, you're looking at them. So the first point here is that what does the age of the moon mean? Well, this is a picture showing, sort of an idealized scenario for the origin of the moon. You start with a protoplanetary disk, you form Theia and a proto-Earth. They collide, they have a debris ring. That debris ring potentially loses volatiles. You form a moon out of the accretion of the debris ring. It melts, it solidifies into a magma ocean, and voila, you got the moon today. So any sort of interpretation of an age has to be done in this sort of general model. But if you look at this in more detail, it's actually a whole bunch more assumptions. There's a whole bunch more ideas that go in here. And so there's a series of processes that I've listed here. I'm not going to read through, but all of these have some impact on the origin and evolution and age that you determine for your system. And so the things that we can actually date include looking at volatile loss by the protoplanetary disk, the lunar disk after the accretion. We can date core formation, and then we can date solidification of various products of a magma ocean. But realize that these ages reflect fractionation of parent and daughter, but they're incumbent on what we assume comes before there. So the timing differences between these things also dictate what the age means. If somebody dates the giant impact and somebody dates magma ocean solidification, they're not going to be the same thing. So first reason things are confused. So more importantly, a lot of the ages that we determine are model ages, and this is a model that I produced looking at the evolution of the rubidium and strontium system in order to define the characteristics of the giant impact and evolution of the Earth-Moon system. So on the vertical axis is a strontium isotopic composition. On the horizontal axis is time. The idea is that you start with that green dot. This is the solar system initial value, and you got to get to that red dot, which is what we argue is the bulk composition of the moon at about 3.5 billion years. So how do you get there? Well, you have a series of stages of evolution. When you hear the word stages, you should be scared, because you have to make assumptions for these. In this case, you have to assume how long that stage lasts and what the parent-daughter ratio is. So in this particular case, I've assumed that the first stages in the protoplanetary disk lasted 2 million years. It had the rubidium-strontium ratio of chondrites. Then I formed Theia and the proto-Earth. They each have their own rubidium-strontium ratios. One I'm assuming is the composition of the Earth today. The other I'm assuming is the same as an angarite parent body. Then these two things evolve. There's a collision during the giant impact. I'm assuming that that occurs in this particular model at 4.42 because this is the uranium-lead giant impact age of Jim Connolly's. I assume that the material forms a debris ring. The debris ring is composed of 90% Theia, 10% Earth. Then we form the moon. The moon has the estimate of the bulk composition of the moon, and voila, I get the moon. So obviously the giant impact is at 4.42 billion years. Undeniable. However, if you look at all the solutions to the model, which this very complicated diagram depicts, you find that there's a wide range of ages. In this particular diagram, the vertical axis is the rubidium-strontium ratio assumed in the model for the bulk moon. The horizontal axis is the age of the giant impact. The green field represents models that assume that Theia had the rubidium-strontium ratio of Angrites. The red is something different. The upper bound of that assumes mixing at 9:1. The lower bound assumes mixing at 7:3. The point is, it's a very confusing plot. You don't need to understand it very well. The point I want you to note is the vertical axis has a large range on it. All of these ages satisfy this model. And as a consequence, I can't use this approach to define the age unless my assumptions are very robust, hence ghastly. So here's another example of a model age. This is a TI diagram. This type of approach was actually developed by a graduate student here at University of New Mexico. If you look at the plot on the right, that's a plot of age on the horizontal axis. On the vertical axis is the initial neodymium isotopic composition determined for a variety of creep-rich rocks. And what Jennifer Edmondson did was she regressed a line through all this data, noted where it intersected with a chondritic evolution model, and said that intersection point defines the age of creep. In this particular case, she got an age of something like 4.34, something like that. Couple of assumptions here that you might be interested in. First of all, you're assuming that the rubidium or all those points are derived 100% from creep, which of course they're not. Second of all, you're assuming a specific evolution model for chondritic meteorites. The green line that you see there is another model that's been proposed and has been used traditionally. And if you look at it closely and squint your eyes, you can see that the intersection of the blue line and the green line is going to be slightly different than the intersection of the yellow line, which is used to calculate the age with the blue line. Hence, you're fundamentally limited here or constrained by what you assume is the bulk composition of the moon. The histogram plots, or the axis ones with the vertical axis that mean nothing, are actually samarium-neodymium ratios that we've determined on chondritic meteorites. And the point to note is that they're highly variable. If you look at these 30 meteorites, the value we get for the bulk moon or the bulk solar system has a 147, 144 value of 0.94. The model, the yellow line, is 0.196. And the green model is 0.1967. So we're making an assumption about chondritic evolutions to basically, 1.1% to define this age. And as a consequence, we're vulnerable. Okay, so ages are wrong sometimes. This was really a beautiful age that I did with Brad Jolliffe. This was the first result. This is a rubidium-strontium age I determined on a classed in an Apollo 12 rock. Beautiful 4.34 kind of age. Everything's linear. Statistics are great. I'm like, wow, here we go. We got it. Next thing we have to do is do the samarium-neodymium. And so this is the results of the samarium-neodymium plot. Roughly linear, a little bit older. Great Nature or Science paper. Ultimately, the problem is that this rock wasn't igneous. It's a mixing rock. It's been mixed. And so what we're looking at is mixing diagrams. So by using one chronometer, we would have never seen this. And instead, we can't date this rock because it's not really a rock that can be dated.
2 minutes.
Okay, sorry. Last example. We've dated an alkali anorthosite. This is a rock that was done by Greg Snyder. He got 2 different ages 20 years ago. We decided, 30 years ago, we could do it a lot better. So we decided to do this. We got some of the rock moving relatively quickly here. The sample is on the picture on the left. It was a very small clast in a breccia. We looked at it like we do everything with the SEM. We noted there's lots of impact melt there, very typical. So we decided to proceed anyway. We dated it, and voila, we did exactly what we said we did. We got concordant ages from 3 different isotopic systems. Unfortunately, the ages were defined by fractions that were dominated by impact melt, and the age was 3.94. Probably sounds a little familiar. So this rock isn't an impact rock at all, or isn't an igneous rock at all. It's an impact melt. We dated it very precisely, but we didn't date what we thought we were going to date. So to conclude, what are we supposed to do here? There's a lot of vagaries here. So you have to select some ages. We need chronology. So what you do is you pick the ages that seem to be most internally consistent, ideally defined by multiple chronometers. You look at, sorry, my eyes aren't good enough to read my own words. So you look for things that are consistent with broader geochemical models. If you get an age that requires you to abandon something like the lunar magma ocean model, you may second guess the reliability of that age. And then finally, I think it's really important to recognize that in order to date something, you have to have very closed and consistent systems, and that most rocks just don't lend themselves to that. And as a consequence, you just have to be satisfied with the fact that a lot of things aren't datable. Thank you.